Okay, welcome everyone to the second part of the Schubert seminar with Kamil Rychlewicz telling us about zero schemes and equivariant cohomology theories. Please take it away.
Thank you. So to tell you something about equivariant cohomology, I will first do a brief introduction uh, to some algebraic group theory. Right, actually, Lie algebras. So this is about constant sections. This goes back to Constant's work from 60s. So that was for semi-simple groups. And then, well, this is not a hard extension, but maybe I should write that together with Tamas Hauser. We also developed this uh, precisely for what we call principally paired groups. And what it actually exactly means, principally paired, is not that important, but uh, the generality which is interesting is that G is a linear algebraic group, which is a parabolic subgroup of a reductive group. So it could be the whole reductive group, it could be a Borel or anything in between. And then G, the group, acts by the adjoint action on the Lie algebra G. And the question, I mean, the whole problem of Constant was how do we parameterize the G orbits? And we could also say G invariants. G invariants. Those are very closely related questions, G invariants on the Lie algebra. And then the results is the following. So there is some affine subspace in the Lie algebra. S in G. So this is what we call the constant section, which has the following properties. First, so this is in G, and if I map this to the quotient of G, the GAT quotient by the group, then this composition is an isomorphism. So S maps isomorphically to the quotient, and S intersects every regular conjugacy orbit in exactly one point. And in fact, S is contained in the regular locus of the Lie algebra. And I should explain what I mean by regular. So an element of the Lie algebra is called regular if the centralizer of this element has the dimension, the minimal possible dimension, which is the rank of G. So otherwise, there's always an inequality. For GLN, in GLN or SLN, this just means that the eigenspaces are one-dimensional. And um, and the first condition, what it implies is that the ring of functions on S. Let me show this. So the ring of functions on S is then the ring of functions on the quotient. So the ring of G invariant functions on the Lie algebra. This, by the Chevalier restriction, this is the ring of Weyl invariants on the Cartan subalgebra. And this is the equivariant cohomology of the point. So I hope this explains why I'm talking about this funny space. And so this means that if I have some G acting on X and I manage to construct some scheme Z such that the ring of functions on Z is the equivariant cohomology of X, then this comes with a map from Z to S. So what we should be looking for if G acts on a variety is something that lives over S. So HG star of the point and HG star of any space, it's graded. So this isomorphism between the ring of functions on S and the equivariant cohomology of the point gives me some C-star action on S, because the grading I can transform into a C-star action. And this can also be constructed purely geometrically, but just what is important is that this action exists. It's definable and it's compatible. So one thing maybe I should also add is that S depends on choices. There are it's not natural, not canonical. And so in the original setting of Costan, where G is a semi-simple group, we take an SL2 triple, a regular principal SL2 triple. And then S is defined as E plus the centralizer of F. So it's a affine subspace. It's a linear space shifted by E. So this depends on the choice of the triple. And then if G is not reductive, if it's, for example, a Borel, then there's some other magic here we have to do. But anyway, it's everything holds. So now if G acts on X, then there is a big vector field I can associate with the action. Yes, I think it's called a slow slice as well. Yes, it's a special case, I think. Um, so so there's a vector field which, for any element of the Lie algebra, is a vector field on X defined by given by the infinitesimal action of that element. If you like a precise definition, then you have the group action. This gives the map of tangent bundles, and then you restrict to the tangent at identity, which is G, the Lie algebra, and here you restrict to the zero section X, and then you see what this maps gives you on this G times X. And then, and so I have this vector field this is a big vector field parameterized by the whole G, and I can also restrict restriction Vs to S times X. And now I define. Okay, so I should write what the assumptions are. So X is a smooth projective variety over C. G, as above, acts on X, and I define Z as the now it's a calligraphic Z. It's a zero scheme of the vector field Vs on S times X. So the picture is that there is this variety X. There's S. There's some zero scheme here, and this maps down to S. Yes, and additionally, so the same comment holds that there's a sister action which I don't want to explicitly define right now because it's slightly technical, but there's a sister action on Z, and that's compatible with the sister action on S. So then I can show that if the dimension of Z is equal to the rank of G, which is also the dimension of S, then O Z of Z, the ring of functions on Z, is isomorphic to HG star of X as graded algebras over this base C of S, which is the equivariant cohomology of the point. And so here I replace the assumption of this E having isolated zeros with the dimension of the zero scheme being equal to the dimension of the base. And this condition is satisfied if E so now E for me means a regular nilpotent in G if E has isolated zeros. So this is the situation which we had before for a Borel of SL2 or SL2 acting. And in that case, Z is even affine and lies within S times 1 Białęcki-Burula cell. So this case was already proved, as I said, by Brun and Carrell for SL2 or Borel of SL2, and then with our joint work with Tamas, it was for general G. So if I go back to this example of Pn, maybe I'll try to copy this. Okay. So this was the vector field defined by the element E in the Borel SL2 on Pn. So here I have Borel SL2. I didn't manage the space very well. Okay, let's say Borel SL2. I write it here. Borel SL2 acting on Pn as before. And now inside the Lie algebra, there is this constant section, which in this case is E plus the Cartan subalgebra. So in other words, this contains all the elements of the form T minus T1, 0. And so then I look at the vector field defined by a general element of this form. And then this vector field, so E, if T equals 0, then I just get E, and I see here the coordinates that I already computed. But additionally, this T variable gives me additional coordinates of the vector field, and they are like this. And at the end, I have minus 2n Vx. And then if you try to solve those equations, then you will see that that Z is spec of C x1, and now there's yeah, I confused T and V, so okay, let me write V here so that now everything is fine. So there's x1 and two coordinates x1 and V, and now the equation is like this. And now it's not just a fig point, so this actually has a dimension, so you can draw it. It's a bunch of lines intersecting in one point. So this here, for example, this is the HC star of P3. And then if you try to do the same thing, but you look at the whole SL2, not just the Borel of SL2, then you will get a similar picture, but you will see parabolas instead of lines. And this is H SL2 star of P3. So this those assumptions of isolated zeros of E, they are satisfied. Um, they are satisfied for flag varieties in general of any type, smooth Schubert varieties. It's quite trivially because they are inside the flag varieties, and Bott-Samuelson resolutions. So all of those examples have the isolated zero of E, and that's maybe slightly disappointing because those spaces we already know cohomology of, and it's not very difficult. But the theorem, or maybe let's say the condition dimension of Z equal rank of G is more general. For example, it holds whenever X has finitely many G orbits. So if G was a torus, then an obvious example would be an toric variety. But for G reductive, we can also consider spherical varieties. And and for spherical varieties, the computation of the cohomology is not that easy anymore. But in fact, in this approach, we see the equivariant cohomology as the ring of functions on something defined geometrically. But the computation is explicit computations are also not easy. Explicit computations are not easy because Z is not affine anymore. So it's not just defined by a bunch of equations in an affine space, and it has multiple components, and it's a quasi-projective variety, neither projective, neither affine, and explicit computation of the ring of functions is not that obvious task to do. But we do have some information, and in fact, this scheme Z might not even be reduced, even though the ring of functions on it is reduced. So it might be a weird sort of a monster. And then one might ask what happens if we go a bit further. So if the dimension of Z is allowed to be larger than the dimension of S, and so in this field there are some derived results. But they look at the whole thing from a very different perspective, and you have to consider derived stacks, and so you don't see anything explicit really. But there is something we can say, and I can also tell you later if you're interested. So let me well, I have 2 minutes, so let me just briefly mention the singular varieties case. So again, if we have G acting if X is a smooth projective variety, and I have G as before acting on X, and Y inside X is a singular G invariant subvariety, then what would be the hope is that we have this isomorphism between ring of functions on Z and the equivariant cohomology of X. We have restriction from here to equivariant cohomology of so this we know under some conditions as above. There is the equivariant cohomology of Y and the restriction map. And what would be the hope is that if I look at Z intersected so Z lies in S times X, so I can try to intersect it with S times Y. So then the hope would be that there is an isomorphism here. But this is not always the case. So the classical, can I take just 3 more minutes?
Yes, yeah, please go
Okay,
ahead.
thank you. So then the classical, well, classical. So then a simple case is when, yeah, so G acts on X with isolated 0 of E. And so this is an assumption, assume. And assume that the restriction on cohomology is surjective. I can even write, it's enough to assume it for non-equivariant cohomology is surjective. Then the dream holds. So then Hg star y is isomorphic to the ring of functions on Z times S intersected with S times Y. But as I mentioned to Leonardo before, you have to reduce this scheme. So it's not enough to take the scheme theoretic intersection. And so this is the theorem. So that was done by Brion and Carrell for the case of SL2, and then by Tamas and me for a more general case. And in the case H, the restriction on cohomology is not surjective. Then H, the ring of functions on this intersection is isomorphic to what I call Hg star of Y, and this is the subring of Hg star of Y generated by Chern classes of equivariant vector bundles. Yeah. And so this can be applied, for example, if inside those PNs with an SL2 action to so-called root coincidence loci, or particular cases the discriminant varieties. So inside PN we look at the locus of all the polynomials that with a double. So we look at PN as homogeneous polynomials into variables, and we look at polynomials with a double root. So this is some singular subvariety, and the cohomology might be not obvious, but we can determine this this subring of cohomology. So it's in some sense the subring which is defined by the geometry. I mean the only things we see geometrically in the cohomology ring are the Chern classes of vector bundles in some sense. And yes, so there are the marginal root coincidence loci in PNs, and then the cohomologies in general, as far as I know, they are not very well known. So this gives some partial access to that. And then there was what I didn't have time to mention is the K-theory, and how we can also see K-theory as rings of functions on some schemes defined geometrically. Then many more things are actually still open questions than theorems, but if you want to know more, you can ask me or look at the paper mentioned before. Yeah, thank you.
Thank you very much. Thank you for a beautiful talk.